All right. Hey there, everybody. This week we are talking about nutrient cycling and soil fertility. So to start off here, let's just talk about the big picture of soil fertility or nutrient management. Our overall goal is to direct the nutrients efficiently between plants and soil, make sure that those things are synced up correctly. So to kind of describe this, we have what we call the 4 R's of nutrient management here. So the first one is right form. So right form means that the nutrient is in a form that is plant available. Not every form of nutrient is able to be taken up through the roots. And so therefore, making sure that the form is able to go through that root is pretty important. Up next is the right amount. We want to make sure that when we have nutrients available to a plant, especially a crop, that we have enough of it. But of course, we also want to make sure that we have enough and in the right form at the right time. Having all the nutrients available, for example, in the middle of winter, would not be particularly helpful for a plant that is not growing in the winter. So we want the availability of those nutrients to sync up with the plant growth stage appropriately. Then also we want them in the right place. You know, nutrients can be either all at the top of the soil, or maybe they're collected in the subsoil, but we need them to be in a place that is available to the plant, right? If a plant can't access them, then it doesn't matter how much is there or if it's in the right form or at the right time. It needs to also be in the right place. So these are called the 4 R's: right form, right amount, right time, and right place. Very witty. So this kind of begs the question, which nutrients are important? Well, there are a total of 17 plant essential nutrients. And by plant essential, what we mean is that without these nutrients, plants cannot grow to reproductive maturity. They can't go through their full life cycle. Now, that's not to say that any one of these is more important or less important. It's that they are all equally important to be able to complete the life cycle of a plant. So the first 3 are carbon, hydrogen, and oxygen. Now the plant takes those up and uses those through photosynthesis and puts those kind of together in the right package through photosynthesis, right? Capture carbon and hydrogen and oxygen in the leaves and fix it, put it together, and convert it into tissues. Next are nitrogen, phosphorus, and potassium. Now these we call the macronutrients. Then we have sulfur, magnesium, and calcium, which are our secondary nutrients. And then we have iron, boron, manganese, zinc, molybdenum, copper, chloride, and nickel. Those are our micronutrients. Some people also say that silicon is a micronutrient, but it hasn't been found to be true for all plants, but for some plants, there's also silicon. Now, today we're going to talk mainly about nitrogen, phosphorus, and potassium, which are our macronutrients, but I want you to know about these secondary and micronutrients as well. We've named these because, macro, those are the ones we need in the most, secondary are in the secondary most amount, and micro plants only need in small amounts. Again, that is not to say that one is more important than the other. This is just about the total mass needed of each of these. So how can we remember so many of these plant essential nutrients? Well, as you might have guessed, I like to use mnemonics and weird little phrases to help remember it. And this one is all about Cyril G. Hopkins. So Cyril G. Hopkins was a soil scientist back in the early 1900s in the neighboring state of Illinois. And Cyril G. Hopkins started he was the father of what then they called agricultural chemistry. We're adding all of these different compounds to soil for plants to be able to take them up. Well, a little story about Cyril G. Hopkins is C. Hopkins Cafe is mighty good. His cousin Mo cleans it by midnight. Nice. So this is how we remember plant essential nutrients. We have carbon, hydrogen, oxygen, phosphorus, potassium, nitrogen, sulfur. calcium, iron, magnesium, copper, zinc, molybdenum, chloride, boron, manganese, stands for midnight, and nickel. Nice. So again, it's C. Hopkins Cafe is mighty good. Cousin Mo cleans it by midnight. Nice. Those are our 17 plant essential nutrients. So we have 17 plant essential nutrients, but what do they all do? So again, as I mentioned, carbon, hydrogen, oxygen are put together in these different forms to be tissues and organic components, and those come from the air. You'll notice that those make up most of the mass of plants, 96% on average. Then we have our macronutrients, nitrogen, phosphorus, and potassium. Now, nitrogen is plentiful in proteins, and it's also in DNA and RNA, right? We have DNA and RNA are nucleic acids, and those nucleic acids have their nitrogenous bases, right? The C, T, A, and G, or U instead of the A in RNA. But those are our nitrogenous bases of different types. Now you'll notice that all three of these come from soil, and they're needed in between 2 to 1%, in that vicinity. Phosphorus, if you remember, is used in ATP, adenosine triphosphate, which is an energy package that we use. It's also in phospholipid membranes. Remember when we did PLFA for microbes? Plants also have phospholipid bilayers. And then again, DNA and RNA have phosphorus in there. There's a phosphorus backbone that forms that double helix of DNA. These are needed about 0.2%, so not super high amounts, but they still need it. Potassium is useful in what we call osmoregulation. That's the regulation of water movement, osmotic potential. We move potassium around, or rather plants move potassium around to create a gradient for water to move into. Again, notice that these are all coming from soil for our macronutrients. Now for our secondary nutrients, we have sulfur, first off, which is really present in proteins. We have, it does a bunch of different things in proteins. Calcium is also important in osmoregulation. And then we have magnesium, which is a central molecule in chlorophyll. Chlorophyll being the thing that helps photosynthesize. And that magnesium helps those chlorophyll, those chloroplasts, to stack one on top of the other and form those thylakoid membranes, if you remember back to biology. So that's magnesium, helps to really organize that there. Then we have our micronutrients, which are a lot of different metals. So we have iron, molybdenum, manganese, copper, zinc, boron, and nickel. So those micronutrients, they're needed in very, very small quantities, less than 0.1% by mass of a plant. And those micronutrients are enzyme cofactors. If enzymes and their substrates that they catalyze are a lock and key, these enzymes help make sure that the key of an enzyme fits into that lock of those substrates. So they make sure that all the things line up and they make those enzyme reactions go much faster. They're catalysts. So this is what all of these different nutrients do, and they all help the plants to complete their life cycle. So, as I've mentioned several times, none of these nutrients is more important than the other. The way that we think about them is which one is needed in greater quantities than another. Now, from an agricultural perspective, we have something called Liebig's law of the minimum. Now, everyone says this is Liebig, but actually it was this other guy, Sprengel, who invented it maybe 20 years before Liebig, but Liebig gets all the credit. Unfortunately, Sprengel is forgotten to the annals of history. But Liebig's law of the minimum says that the nutrient that is available in the lowest relative amount is the one that limits plant growth. So back in the day, they had a lot of barrels, and so he liked to use a barrel analogy. What he said was you can only fill up a barrel to the shortest stave, and the stave here being an analog for a nutrient. And the water in the barrel is an analog for the crop yield. So for example, It doesn't matter how big all of these barrel staves are. If this one's the lowest, that is the highest amount of yield that we can possibly get for that crop. So for example, if you have lots of nitrogen, phosphorus, and potassium, but you don't have enough calcium, if your calcium is the lowest stave here, then you can't yield anymore, no matter how much more nitrogen or phosphorus or potassium you have present for plant available uptake. So that's the law of the minimum, and that has really guided a lot of soil fertility decisions for the last, we'll say, 100 years or so. So where do these nutrients come from? We kind of briefly mentioned that most of them come from the soil, but let's dig down into that a little bit more. So they can come from added fertilizers. Now that can be synthetic fertilizers or mineral fertilizers, as we call them. So those could be things like liquid fertilizer, urea ammonium nitrate is, for example, a synthetic one. You could also have mineral fertilizers, so things like phosphate rock get added, or different variations of phosphorus. Those are just minerals. You can also have organic fertilizers. So those are your things like compost, manure, etc. So organic meaning that it's bound up to some sort of carbon molecule. But there are also kind of inherent soil nutrients. So going back to our first lecture, we have the weathering of these soil minerals, right? And that weathering makes it so that some of these nutrients can become available. Things like, say, potassium or iron, or any of those sort of micronutrients especially come from inherent soil nutrients. There's also the soil organic matter, kind of that inherent in indigenous soil organic matter, that native soil organic matter there, also is a source of nutrients for plants. These are kind of in a consistent ratio in that soil organic matter. It's not to say that this happens all the time, but there's a general tendency for soil organic matter to have this predictable ratio. And that ratio is 100 parts of carbon to 10 parts nitrogen to 1 part phosphorus. If you remember back to the microbial biochemistry lecture, that this ratio differs between the inherent soil organic matter and that soil microbial community within that biomass. Now, just generally speaking, when you have those that organic matter with those associated nutrients, there's kind of two opposing processes. So the first one is called mineralization. Now, mineralization is the process of breaking down that organic matter and making those nutrients available to plants in that right form, right? And we call it mineral form because it mimics the minerals that come from, say, phosphorus or nitrogen, et cetera. And it's in this smaller, more mineral form, and it's no longer bound to carbon or oxygen or anything like that in these organic molecules. We also have an opposing process called immobilization, which is where these plant available nutrients, those mineral nutrients, are then taken up and mostly by microbes. And again, it becomes part of their biomass, and those microbes live and die and they become part of the organic matter. But both of these processes are microbially mediated. This is part of why we call soil microbes the eye of the needle through which all nutrient transformations must pass. So these two processes are constantly going on. It's not all of one or all of the other, but it's about the relative ratio of those two processes. The most complicated of soil cycles is probably the nitrogen cycle. So this is a simplified version of it, but it gets most of the major processes. So the major source of nitrogen on Earth is atmospheric nitrogen, nitrogen in the form of N2 gas, dinitrogen. And that makes up about 78 to 80% of our atmosphere is made up of this N2 gas. Now, that N2 gas gets fixed into these different organic forms, and that requires a lot of energy. We can do that artificially through what we call the Haber-Bosch process. But then also there are rhizobia, which are microbes that are associated with plant roots that can fix it. They also have free-living microbes that can do this nitrogen fixation. Also, another source is lightning can strike and you get this N fixation. Now, lightning is a pretty insignificant contributor to that, but it just kind of goes to show exactly how much energy is required to convert that nitrogen into some more easily accessible forms. You know, N2 is an N with 3 bonds between it, an N triple bond. And so that takes a lot of energy to break all 3 of those bonds. But then once it is, you have it in the organic N form. So organic N refers to things like amino acids, and you put those together to make larger proteins. And those are called organic because they're, again, bonded to different carbon molecules. Now here is, as I just discussed, that mineralization and immobilization is a microbial process, and it's constantly going back and forth. But that mineralization process converts the organic nitrogen into ammonium, or NH4+. Now, NH4+ is a plant available nutrient. Plants can take that up, and this is in fact energetically preferred. But that ammonium can then be further processed by microbes in a process called nitrification, converted to nitrate. This process generally is much faster than the mineralization process. And so there's not a lot of ammonium in soil usually. Most of this nitrogen is in the form of nitrate because plants just can't really compete with microbes as this process happens. So then we have nitrate. Like I said, nitrate is also available to be taken up by plants. Nitrate is also very water soluble, so it can move pretty easily throughout the soil, whereas ammonium is positively charged, and so it sticks to that cation exchange complex more readily. Then finally, to complete this cycle, we have something called denitrification, which is where nitrate gets converted to N2. This is again a microbial process. Now remember back to our preferred electron acceptors, right? Oh no, my feet so cold. Nitrate is the electron acceptor, and it gets converted to N2. That requires a lot of energy, again, to convert it into N2, and it's a very specialized microbial process. Now, this nitrogen cycle is kind of leaky, and so there are a couple places where we can actually lose nitrogen to the environment. So the first one is a process called volatilization. Now, volatilization happens when ammonia gas, which is NH3, comes off, and you can see that NH3 is a pretty similar molecule to NH4, ammonium. And so what happens here is that we go from this solid of organic N into a gaseous form, and you can smell that ammonia gas smells not so good, so you might be familiar with that smell. Another source of losses is in nitrate. Like I said, nitrate is very soluble, and so it leaches, and that leaching means that that nitrate ends up in either surface water or groundwater. So if you have runoff or if you have deep percolation of water, you can end up with nitrate in those, and that causes all kinds of problems. If it's in surface water, you can cause eutrophication, which is when lakes turn green, or in the Gulf of Mexico, that dead zone. And then you can also end up with nitrate in the groundwater. And when you have nitrate in groundwater and it ends up in your drinking water and it goes untreated, that can be carcinogenic and cause something called blue baby syndrome. So nitrate in groundwater is a pretty significant issue in places that rely on groundwater for drinking water. Another source of nitrogen losses in this kind of leaky cycle is through something that's called incomplete denitrification. So that nitrate doesn't get converted all the way into that stable N2 gas, and it goes kind of partway and it becomes N2O, or nitrous oxide. Now, nitrous oxide is a potent greenhouse gas. It has the potential to the greenhouse gas warming potential. That's almost 300 times, about 296 times that of CO2. So on a mass basis, N2O has a greater potential for global warming than CO2. So this is another potentially problematic loss of nitrogen from this nitrogen cycle. So When we talk about nitrogen and that organic nitrogen mineralization process, how to decide if something is going to mineralize or immobilize? Well, we like to think of that in terms of this balance between carbon and nitrogen, or we call it the C to N ratio. And we use that as a general rule of thumb to predict whether that organic compound will be a source of nitrogen for a plant or a sink, that is, whether it will provide nitrogen for the plant to take up or whether it will take up the nitrogen and compete with the plant. And in general, lower C to N ratios provide more nutrients than higher C to N ratios. Remember that soil microbial biomass has the ratio that it's kind of looking for, if you will, of 8:1. And so similarly, we want to, a lower C to N ratio makes it so the microbes prefer to break that down. It's a little bit easier to break down. So what happens is at high C to N ratios, we get immobilization, right? So if you have in the range of, say, 60 to 40 or so, you will definitely get some immobilization. And what happens is if microbes are more likely to be N-limited, and so what they do is they will burn through that organic matter and they respire that CO2. Remember, they mineralize it and they are breathing that out as they are working hard and they're building their biomass. So when they build up their biomass, they're taking up nitrate and making more little microbes. So then that process kind of slows down as your C to N ratio decreases, but CO2 kind of comes up and then peaks and comes back down. And then eventually what happens is that you get net nitrate production. You see here that we're a little bit higher in the terms of nitrate production than we were before. And that's as that excess carbon relative to the amount of nitrogen gets burned off, right? Here it gets burned off. That then you start to actually produce, okay, we don't have, microbes have more nitrogen than they need. And so they will have net nitrogen production for plants to take up, which is where that net mineralization takes over. So when we talk about the 4 R's as it relates to nitrogen, one of the most difficult ones is to make sure that we're getting it at the right time. So what happens is, as I just kind of described a little bit, we have that mineralization of organic matter that's happening. Now, from a crop production perspective, we put on some sort of, say, organic amendment. Maybe it's compost, maybe it's manure, maybe it's residues from the year before, maybe it's a cover crop, all kinds of different organic amendments that can come in to a system. So those come into the soil and immediately microbes start breaking it down and they mineralize a whole bunch of that and convert it into plant available nutrients. However, the timing of that is, because that happens pretty quickly and then attenuates as time goes on, the plant isn't very big yet to be able to take that up. Its nitrogen needs are not that great. So as the plant gets bigger and bigger and it needs more nitrogen and its roots are able to take up that nitrogen, only a little bit of those inputs are able to actually become plant available at the right time. So you see here, just this tiny little area here is the amount of that overlap between these two curves is what ultimately becomes taken up by plants. And so there are lots of different strategies that we try from a nutrient management perspective, try and get those two curves to overlap with one another a little bit better. But it really is challenging. And we call this the synchrony problem, or more specifically, asynchrony. We're trying to get these two curves of production and uptake to match up. So moving on from nitrogen to our next macronutrient, which is phosphorus. Now, the phosphorus cycle is a little more straightforward than nitrogen, but there's still a lot of trickiness here. So let's start with organic phosphorus. Now, organic phosphorus, we can think of it as kind of this continuum. So we have our more stable organic phosphorus. So this would be like phosphorus diesters. Those are more stable phosphorus. And then those get broken down by enzymes and they become more and more labile or more and more accessible. Then, similar to nitrogen, that phosphorus can be mineralized and immobilized. again, a microbial process there, and it comes into what we call solution phosphorus. And that solution phosphorus is what plants can take up. Now, when it comes to phosphorus, there's a pretty significant role of chemical sorption. So phosphorus can be present in primary minerals, things like apatite, which is a calcium phosphate, and then those minerals dissolve and weather, and then eventually we just have phosphate that's kind of stuck to the clays. Look, these have ammonium, or sorry, have H+ ions on them, and they can kind of get stuck to the clay, and they're kind of in this dynamic equilibrium with solution phosphorus of sorption, desorption. Now, similar to nitrogen, phosphorus can get leached or run off, and it can go into surface or groundwater, again, causing problems like eutrophication or when the lakes turn green in the summer, et cetera. So that is a potential source of solution phosphorus loss as well. Now, solution phosphorus, we need to think more about another R, which is the right form. And what happens is, because phosphate, the PO4 molecule, can have H+ ions sorbed to it, it kind of, as soil pH changes, the relative amounts of it in the solution can vary. So you can see as one goes up, so for example, at a lower pH, we have more H+ ions, and we're more likely to find the phosphate in the form of H3PO4. Now, as pH goes up, the relative amount in that form goes down, and it becomes more of it is in the H2PO4 form, and we just have the H+ ions kind of in solution. So you can see that goes up, and then that also goes down as the PO4 with a 1H becomes more common. And then similarly, at high pHs, we can find PO4 without any H+ on it dominates. It's important to note that H2PO4 and HPO4 are the most readily taken up by plant roots. So those are kind of more prevalent at these circumneutral pHs, right? You can see that that's maybe between pH 9 and pH about 5 is when those predominate. Now, phosphorus, when it's in solution though, remember, it's sticky. It sorbs to those soil surfaces pretty readily. So that sorption, as we remember back to our soil chemistry unit, remember that sorption is very pH dependent. So what happens is a lot of the phosphorus that is in solution ends up getting stuck on to other things or forming complexes with other compounds in soil. So this is, again, pH dependent. So at lower pHs, you can have that phosphorus binding to things like iron and aluminum and manganese to form these different compounds that are not plant available. Similarly, here you can see that phosphate reacts with silica and silicate minerals. Remember that silica is a really common soil mineral. It's one of our layers of clays. And then at higher pHs, phosphates will kind of fixate with calcium phosphates of different forms. So what it means is that, first off, most of the phosphate is not actually plant available. You see that it's probably about maybe 20% of the total ends up being plant available. Moreover, it is really pH dependent, and it really is maximized between around, say, pH 5.5 and pH 7 is where the pH where phosphorus is maximally available. So people do all kinds of things to make sure that phosphorus will be available, things like liming and to raise the pH in acidic soils, things like that, just to make sure that phosphorus is in fact plant available. So we're talking about nutrients, and their availability to plants, but then those nutrients end up getting removed when we have something like a crop, right? You harvest your corn, you harvest your wheat, whatever it might be, and then you take those nutrients off the field. And so something of interest is how quickly different crops will remove those nutrients, right? And remember, we were talking about right timing, and you can see that throughout the season, this is a corn uptake of nitrogen. You can see that throughout the season, it varies. Again, remember, starts off slow and then the rate increases and then it kind of levels off again. And you can also see here, it shows you where those nutrients are actually going in the plant. Notice that the first little bit, it's all in vegetative growth, things like the stalk and the leaf, etc. And then towards the end of the season, when grain is filling out, you get lots and lots of nitrogen going into there. But the rate of other things, for example, phosphorus going with it, is somewhat consistent by crop. So if we look at something like corn, you're losing about 0.67 pounds of nitrogen per bushel of crop. So if you have a 200 bushel an acre harvest, you're losing about 120 pounds of nitrogen, something like that. Similarly, phosphorus comes off in these somewhat fixed amounts. And you can see that not every crop is taking up the same amount of nitrogen. Some are much more nitrogen hungry than others. So for example, here we have soybean is about 5 times as much nitrogen as corn. Now, soybean being a legume has those rhizobia and is able to fix a lot of that nitrogen for itself, but it still is removing a lot of nitrogen per bushel. Similarly, wheat, right? Wheat is fairly high protein in it, and so it's pretty nitrogen hungry as well. And so you see that it's removing more nitrogen per bushel than other crops. Corn and rice are more carbohydrates, I should say, and so they have less nitrogen in them. You can similarly see that phosphorus varies. And again, soybean is pretty phosphorus hungry, and wheat is also as well. So to review, when we talk about nutrient management, we have the 4 R's, which are the right form, right place, right time, and the right amount. So we want to make sure that we get our nutrients in the right form, at the right place, at the right time, at the right amount. That's the 4 R's, all in a nutshell right there. When we talk about plant essential nutrients, there's carbon, hydrogen, oxygen, which come from photosynthesis. So we don't need to worry about managing those as much. The plant can take those up from the atmosphere. But the ones we do need to worry about are these other ones. So we have nitrogen, phosphorus, and potassium are our macronutrients. And again, we call them those not because they're more important, but because we need them in greater amounts. Then we have sulfur, magnesium, calcium are our secondary nutrients. And then we have other nutrients, iron, boron, manganese, zinc, copper, chloride, and nickel, which are our micronutrients. We went through both the nitrogen and phosphorus cycles, and just to kind of sum those up, the nitrogen cycle has both biological and chemical processes happening, but biological processes dominate. And a lot of those changes in the nitrogen form are microbially mediated processes. Then we have the phosphorus cycle, which again has both biological and chemical processes, but unlike the nitrogen cycle, chemical processes dominate. Its absorption and desorption are the name of the game, and it's very pH dependent. So with that, we'll leave it there for this week. Thanks, everybody.